Greetings, class. Sherman and I today are going to pick up where we left off on the last video, our intro to stoichiometry video. And we're going to go over how to do some other types of stoichiometry problems, okay? In the first video, we saw how the mole ratio can be used to calculate the number of moles of a participant that we want to find out about. And once we find moles of that participant, at the very end, we kind of touched on how once we know moles of, for example, aluminum oxide, we could calculate mass of aluminum oxide using the molar mass, or particles of aluminum oxide using Avogadro's number. Okay, it turns out that there are many kinds of stoichiometry problems, not just ones where we calculate moles, as we did on the last worksheet. And so we're going to be learning in this video, part 1 and part 2, how to calculate mass, particles, and volume. Now, because that's a lot of units, we've done moles already. We're going to learn how to calculate mass, particles, and volume. What I'm going to need to do to make this make sense, so I'm going to give you today a template for solving stoichiometry problems that will allow you to easily deal with no matter what units you're presented with, units of moles, mass, particles, or volume. Now, so what I'd like to do now is just kind of look at the type of problem we've done so far. And this is a repeat of a problem that we did in the last video, okay? How many moles of aluminum oxide? And so notice that this how many moles of aluminum oxide, that is the substance that I want to find out about. And what we're going to do is we're going to call the substance that we want to learn about or calculate, we're going to call that substance B, okay? And so in the balanced equation that I have here, I'm going to write B here, and because I want to calculate moles, I'm going to put a blank line here. I'm going to put moles, and then you can put a question mark in there if you want, because to represent the how many. And then the problem goes on. Would be made if 0.882 moles of oxygen reacted in this following balanced equation. Well, notice how this is a given amount. I gave you that amount. We're going to call the given amount, that substance, we're going to call substance A. I'm going to mark substance A here, and you notice that I wrote 0.882 moles. That's the amount of the given substance, oxygen. And when we look at the units for the given substance and the desired substance, the one we want to find out about, we can actually see why we might call this kind of problem a moles of A to moles of B problem. And this is how we're going to designate our stoichiometry problems, based on the units for the given and the units for the desired substance. But we'll see that on the next page of notes. If you recall, then the way we solved this problem in the past was we started with our given. We applied that magic mole ratio, the mole ratio, which was the coefficient of aluminum oxide over the coefficient of oxygen. And the reason we did it like that was so that the units moles of oxygen would cancel. And so you can see we started out in our stoichiometry problem here with the units being in terms of substance A, moles of oxygen, that was substance A. And using the mole ratio, though, we've actually turned that unit, because of the cancellation here, into moles of substance B. And that's really what the mole ratio does. It shifts the problem from being in terms of a given amount to being in terms of the desired quantity, or what we want to calculate. Okay, so let's go on, and now that we've reviewed the previous kind of stoichiometry problem we've done up till now, let's sort of go through a 6-step stoichiometry problem-solving process that we'll be able to use every single time, no matter what units of our A or what units of our substance B our problem entails. Okay, let's get started. Gentlemen, I would recommend that as I'm going through these 6 steps that you write them down in your notes, because down below this I have the same sample problem as on the previous slide, and what I'll do is I'll sort of relate these 6 steps to that problem. Okay, so first, anytime you go to do stoichiometry, you have to have a balanced equation. And the main reason for that is, if you recall, those coefficients in the mole ratio come from the balanced equation. So you need to have a balanced equation. Then what you're going to do is you're going to look at the stoichiometry problem and determine which substance in the chemical reaction I gave you the information on, and we're going to call that substance A. And then which substance in the balanced equation I want you to calculate the amount of, and that's what we call our desired substance, and that's going to be substance B. Then what you're going to do is you're going to look at the units given for A. Is it moles? Is it mass? Is it particles? And you're going to look at the units that we want to calculate the amount of substance B in, for example, grams, particles, liters, things like that. And that's going to allow us to what I call diagnose the type of stoichiometry problem. In other words, are we starting off with moles of A and wanting to calculate mass of B? Are we starting off with moles of A? Maybe we want to calculate particles of B, all right? And this step number 3 is extremely important because it's going to basically drive the entire stoichiometry problem. The units that we're given and the units that are desired, you'll see, are very much key to solving stoichiometry. All right, let's say that we don't start off with moles of A. If we don't start off with moles of A, what we want to do is we want to convert whatever units we're given, mass, particles, volume, we want to convert that to moles of A. Because once we get to moles of A, we're going to be able to apply the magic mole ratio. Why do I call it magic? Because as we saw in the previous example, the mole ratio allows you to kind of convert or shift your problem from being in terms of substance A to being in terms of the amount of substance B. And substance B is what we desire to calculate. Remember, the mole ratio is always the coefficient of B over the coefficient of A from the balanced equation. Finally, once the mole ratio gives us moles of B, we can use moles of B to calculate, maybe we want to calculate mass of B. Well, from moles to mass, we'd use molar mass. Let's say we may want to calculate particles of B. Well, we'll take the moles of B and use Avogadro to calculate the particles of B. And again, we're going to touch on volume in this lecture. We won't be talking about concentration. Concentration we will talk about when we do solution chemistry, and we'll be talking about concentrations of solutions. So let's apply this 6 steps to the problem that we just did on the previous slide. Okay, so how many moles of aluminum oxide? Because I said how many. This is my desired quantity. I'm going to label it B, and I label it B in the balanced equation. Would be made if 0.822 moles of oxygen reacted. Again, that's my given. You see how I mark that. Then, well, I already have moles of A, so I don't need to convert to moles of A, but I have moles of A. I'm going to start with that. The step after moles of A, you apply the mole ratio. Notice that the mole ratio is the coefficient of B over the coefficient of A from the balanced equation. That's our mole ratio. And again, we can see that with our mole ratio, that moles of oxygen cancel out, and what we're left with are moles of B. Well, let's say we wanted to calculate mass of aluminum oxide. We would just take these moles and multiply by the molar mass of aluminum oxide. But we only wanted moles in this case, so we can stop here. So what I'd like to do now is on the next page, go through some of those different variations in stoichiometry problems where we work with mass, where we work with particles, and finally where we work with volume. Okay, class, let's go through some sample problems that will introduce mass, particle, and volume stoichiometry. Let's look at our first problem. Number 1. How many grams of oxygen? So you see I marked that because I said how many, that's my desired quantity. So I marked it as substance B. I marked it in my balanced equation, and I put how many grams. Let's go on. Are needed to react with 0.640 moles of iron. That's my given substance. So following the 6-step process, I had my balanced equation. I figured out what my given substance and what my desired substance is. And not only that, but I also included the units, as in step 3. I'm given moles and I want to calculate grams of oxygen. So to diagnose this, it's a moles of A to mass of B stoichiometry. Again, whenever I think of mass, in the back of my head, I'm thinking molar mass. And so then I'm thinking that at some point, I'm going to need the molar mass of oxygen. So I'm going to start my problem with my given 0.640 moles of iron. My units are starting out as units of moles of A. So I don't need to convert. I already have moles of A. I don't need to convert mass of A to moles of A. So I'm good starting with this. After I have moles of A, the next step says use the mole ratio from the balanced equation to convert moles of A to moles of B. So I've written in my mole ratio. Notice that this is the coefficient of B over the coefficient of substance A. Then I see that by applying my mole ratio, essentially my units of moles of iron cancel, and so now everything is in terms of moles of substance B. I don't want moles of substance B though. I want, in this case, I want mass of B. But once I have moles, I can use the molar mass of B, the molar mass of oxygen, to calculate the mass of oxygen. So let's do that. So the molar mass of oxygen, 2 oxygens added together because it's O2. Molar mass is 31.998 grams per 1 mole of oxygen. So I wrote in my molar mass so I could convert to the desired units of mass. Then you can see that the units of moles of oxygen cancel out, and what I'm left with is, units of mass of substance B. And that's what I wanted. So I can stop here and now do the math. So I would take 0.640 times 3 divided by 4, because it's in the denominator, times 31.998. I get 15.3590, blah, 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 in my calculator. And because my initial value, my initial given started out with 3 sig figs, I'm going to round my final answer to 3 sig figs. So the final answer, the number of grams of oxygen needed to react with this many moles of iron would be 15.4 grams of oxygen. Okay, let's look at sample problem number 2. How many grams of oxygen? Once again, oxygen then is substance B. I'm going to mark B. I'm going to say how many grams are needed to react with 30 grams of iron. So this is my given, 30 grams of iron. I'm going to mark it A. I'm going to mark iron as A in my balanced equation, and I'm going to say 30.0 grams. So I've determined my A, my B. I've looked at my units for A and for B. And so I'm going to diagnose this as a mass of A to mass of B stoichiometry problem. Mass of A to mass of B. Again, when I think of mass, I think of molar mass. So I'm probably going to need the molar mass of substance A, iron. I'm going to need the molar mass of substance B again, oxygen. So I'm going to start with what I'm given. And notice that I'm not given moles of iron, I'm given mass of iron. And so the first thing you need to do when you're given a different unit is you need to convert whatever this unit is, get to moles of A. So we need this to be moles of iron, moles of substance A. So to do that, we're going to use the molar mass of iron, and we're going to divide by the molar mass of iron to get moles of iron. So when I do that, notice that the units grams of iron cancel, and what I'm left with is moles of iron. The next step in the problem solving strategy says once you have moles of A, use the mole ratio to get the equation here in terms of substance B. So I'm going to put in the mole ratio. Again, the mole ratio, it's the moles of B from the balanced equation over the moles of A from the balanced equation. Okay, when I apply my mole ratio, notice that moles of iron cancel, and the units I'm left with at this point are moles of oxygen. Now that's pretty good, because once I have moles of oxygen, I can fairly easily calculate mass of oxygen using the molar mass of oxygen. So there's my molar mass of oxygen, 31.998 grams oxygen per 1 mole of oxygen. I look at my units and I see that, again, moles of oxygen cancel. I am left with mass of oxygen, that is mass of B. Look at that, grams of oxygen. That's what I desired. So now it's all over, but doing the math. So we take 30 divided by 55.845 times 3 divided by 4 times 31.998 and round it to 3 sig figs, which is the number of sig figs in my starting amount, 12.9 grams of oxygen. So to react with 30 grams of iron, I would need 12.9 grams of oxygen according to stoichiometry. Let's do a quick rundown of that problem once more. So we started out with mass of A. We used the molar mass of A to convert to moles of A. Then we used the mole ratio to go from moles of A to moles of B. Once we had moles of B, when we wanted to calculate mass of B, we used the molar mass of B to get to our final answer, 12.9 grams of oxygen. Sweet. All right, let's move on to sample problem 3, which is going to involve particles. So it's going to bring in Avogadro into the mix. All right, the problem says, how many particles of Fe2O3? Well, how many? That's my substance B. I'm going to mark this as substance B. I'm going to say, how many particles? Again, particles, I'm thinking Avogadro. Oh, how many particles will be made when 30 grams of iron react? Okay, that's my given amount once again. That same 30.0 grams of iron. This is substance A because that's my given substance. Okay, looking at our diagnosis, this is a mass of A to particles of B, stoichiometry problem. So mass, again, I'm thinking molar mass. I'm going to need the molar mass of iron. Particles for Fe2O3, I'm going to need Avogadro. Now before we go ahead and set up the solution to this, I just want to point out that if you notice, this is the first time that we're actually calculating the amount of one of the products. In the previous 2 examples, we used the amount of iron to calculate the amount of oxygen needed. Guys, whenever you calculate the amount of a product using stoichiometry, stoichiometry predicts the exact amount of that substance you should make. And because it predicts the amount that you should make in theory, whenever you calculate the amount of product using stoichiometry, that amount is going to be called the theoretical yield. So in this problem, I could have said, what is the theoretical yield of Fe2O3 in particles when 30 grams of iron reacts? Or I could say, how many particles of Fe2O3? Either way, whenever you calculate the amount of product using stoichiometry, because for product we always think of yield, like yielding crops, we're yielding product. But because this is done using stoichiometry, and stoichiometry predicts what you should make in theory in this chemical reaction if it were perfect, it's called the theoretical yield. So you'll see that term come up now and again, theoretical yield. In fact, it's going to come up in the first stoichiometry lab that you guys work on. Okay, let's get this solution going. So again, I always start with what I'm given. In this case, 30 grams of iron. I know that my first step is to go from whatever units of the given material, I need to convert that to moles. And the way I go from mass to moles is using the molar mass. In this case, the molar mass of iron. So I applied my molar mass. Again, we want to divide because we want mass to cancel and we want to be left with moles. And so this got me moles of A. After I applied my molar mass, I'm at moles of A. In my problem solving strategy, it says once I have moles of A, what do? I use the magic mole ratio to turn A into B, apples into bananas. And that mole ratio is always the coefficient, in this case B over here, over the coefficient of A from the balanced equation. Again, there's my mole ratio, coefficient of B over the coefficient of A. Again, in that step, moles of iron cancel. I used my mole ratio. I went from moles of A to moles of B. Look, the units that are left after those units cancel are the moles of B. And once I have moles, how do I get to particles of B? Well, particles of B, Avogadro. Let's plug in our Avogadro's number and get our particles of B. Again, there's Avogadro's number. Moles of Fe2O3 cancel, and what am I left with? Particles of Fe2O3, which is what I wanted. Cha-ching! Done. It's all over, but doing the math. So 30 divided by 55.845 times 2 divided by 4 times Avogadro. Round the 3 sig figs, which was my sig figs in my initial starting amount, 1.62 times 10 to the 23rd particles of Fe2O3, which by the way is rust. Okay, now we're going to stop the video here. We're going to go on to part 2. We'll start up with part 2 in a little bit. And then in part 2, we'll be tackling volume.